Yeah. Okay, so thank you for the introduction. I am Elizabeth Martin Jefremovas. I come from the University of Cantabria, and my work is the work I'm going to share today is going to be about the observation of surface magnon and crystalline electric field shift in superantiferromagnetic neodymium copper 2 nanoparticles. So the outline of the talk is going to be the following. First of all, I will briefly set the context and motivation about the research we carry out in Santander. Then I will explain a little bit of the experimental techniques involved in this work. And the main part of the work is going to be focused on the results and discussion of the discussion of the results, of course, which encompass both structural characterization made by means of X-ray diffraction and neutron diffraction, and the inelastic neutron scattering part. And then we will finish by raising some conclusion of the works. So, in Santander, we are studying currently two kinds of magnetic system. Ones where the magnetism arises from the 4F orbitals, which are the rare earth intermetallic and the RKKY exchange interaction, and the other one where the magnetism arises from the 3D orbitals, which is about ferrum oxide, and more precisely to magnetotactic bacteria, which are made in collaboration with our group, with the group of Professor Maria Luisa Fernández Gubieda at the University of Basque Country. Well, the work I am going to show today is related to the former rare earth intermetallic alloys. So this kind of binary alloys, when alloying a rare earth with aluminium, this gives rise to a ferromagnetic coupling. And on the other hand, by replacing the aluminium by copper, the coupling changes from ferromagnetism to antiferromagnetism. In both cases, when these bulk alloys are nanoscale, frustration and disorder emerge, and a spin glass disorder phase is established in the alloy. So our previous work on terbium and gadolinium revealed the coexistence of both antiferromagnetism and spin glass at the nanoparticles, giving rise to a state that is known as superantiferromagnetism. So the question here in this work is, well, we just wonder about what about neodymium copper 2? And why neodymium? Well, first of all, it must be taken into account that neodymium ions are chromers. This means that the crystalline electric field splitting is made of doublets instead of single levels. This means that if you are in a magnetic field, these doublets are going to split, and you are going to see if there is or not any magnon excitation or spin wave propagation in the alloy. And also, neodymium offers another advantage, which is that it only has 5 doublets, 5 crystalline electric field doublets, which is very, let's say, user-friendly, because there are others that are up to 20 crystalline electric field levels. And also, in this alloy, there is a low phase temperature antiferromagnetic phase, which is commensurate. And we have observed, thanks to the magnetic measurements, that there is an emergence, an onset of a spin glass phase at the nanoparticles. So the question that are going to be faced is, first of all, whether the crystalline electric field remains or not at the nanoparticles, and of course, if the nanoparticles keep this superantiferromagnetic structure or not. Well, regarding the experimental techniques, first in Santander, we produce the nanoparticles by first the alloys were produced by arc furnace, and then they were nanoscale via ball milling. The structural characterization was made by means of X-ray diffraction, and the magnetic measurements were made by SQUID, by using a SQUID MPPNS. And then, on the other hand, of course, accessing neutron means that you need to access large facility, which in our case was the neutron diffraction was performed at LLB in France, and the inelastic neutron part was performed at ILL, also in France. So I will start with the structural characterization, and first of all, the X-ray diffraction. This characterization, and also thanks to the Rietveld refinements, we determined that the crystalline structure was well preserved in the nanoparticles. And also, we achieved nanoparticle size of around 18 and 13 nanometers for 2 hours milling and 5 hours milling, respectively. So, regarding the neutron diffraction, first we perform refinements on the paramagnetic region just to verify that the nanoparticle size meet congruently with the former obtained by means of X-ray diffraction. We also observed that while the temperature was low then and even more, once in a magnetic state, there is an enhance of the unit cell contraction, which means that which reveals somehow that there is an existence here of magnetoelastic effect, which is very common in rare earth, in rare earth alloys. So the most interesting thing came when we performed the ripple refinement on the magnetic state, on the low temperature magnetic state, where we observed that the magnetic peaks, the peaks associated to the magnetic structure, remain also at the nanoparticle. This means that and even more, these peaks were well modeled with a commensurate square-up modulation in the same way as the bulk alloy. Here I have included a little sketch on the magnetic unit cell, which includes, which encompasses up to 20 20 crystalline unit cells. But now we decided to go one step beyond and to study the energy excitations in the nanoparticles. We only gain access, or we only have enough beam time to measure the 5-hour mill nanoparticle. This means the smallest ones, and we decided to go through three temperatures and 3 different incident neutron energies to have a complete chart of the excitations. In this talk, I will focus on the paramagnetic region at 10K and in the low temperature region well below the Nernst transitor. And to do the fittings, we decided to use a Gaussian boot shape of the plastic battery excitation.
If you have any hurry.
Sorry, have you?
You have 1 minute left.
Sorry?
You have 1 minute left.
I thought that the talk was about 10 minutes, isn't it?
8 minutes.
Okay. Okay, so I will run up. So this is about the bulk state, okay? So I will skip maybe the bulk state, and if you have some question, just ask me. Because the most interesting part was concerned to the nanoparticles, where the bulk peaks remain. And what is more, we decided to separate the surface contribution from the total nanoparticle, just to see whether the crystalline electric field excitation and magnon remain at the surface, not just at the nanoparticle state, but at the surface. And what we observe is that these crystalline electric field peaks remain at the nanoparticle, so did the magnon excitation, this is absolutely unprecedented for 4F based nanoparticles. And there is a little shift of the magnon due to the anisotropy, which is a really striking result, at least from my side. So the conclusions are just that the nanoparticles remain the same bulk crystalline structure. Also, they remain the bulk commensurate square-up modulation, the same magnetic structure, and the crystalline electric field excitation are also present not only at the nanoparticle, but also at the surface of the nanoparticles. And of course, I will end this talk by just saying moltes gràcies per la seva atenció. And of course, if you have any question, I would be very pleased to answer them. And sorry for this misunderstanding, misleading about the time.
That's okay. So any question?
I would like to ask if there is any contamination coming from the ball milling process.
No, there is not. This is, we are using carbon tungsten in the milling, And there is no contamination because we have this procedure is well standardized. It's not the first time we do it, and we have been very careful about that. And there is no contamination.
Okay, thank you.
Any question? So I have a question that you mentioned that is spin glass. So spin glass, does it influence the structure of the material or the properties?
Yeah. There is a spin glass phase at the surface, yes, and this is why you have to speak about superantiferromagnetism. The antiferromagnetic structure is within the core, and the spin glass it just takes place at the nanoparticle surface.
Okay. So let's answer Elizabeth again, and let's welcome next speaker.
Thank you.